This video is presented by Rokio, an early-stage Bay Area company introducing a new, exciting, patented, and proven form of artificial intelligence that we call direct learning.
Imagine that you can simply point and your computer, robot, or machine will learn. No costly analysts or engineers. In hours or days, your application is ready to export, and your application can be embedded on small devices or function at a large scale.
Direct learning is built for real-world data. Real-world data are images, videos, and waveforms from cameras and sensors that are ubiquitous in our modern world. Direct learning learns directly from the camera or sensor output. No complex algorithms, no lengthy process. Deep learning is the dominant form of artificial intelligence today. Deep learning has made fantastic strides over prior artificial intelligence models, enabling machines to play chess, drive cars, trade stocks, make discoveries, and help businesses run better. But deep learning is also complex, costly, and as we will see, prone to occasional, inexplicable, and potentially dangerous error. The differences between deep learning and direct learning are numerous and appear stark, but are these important differences? Can direct learning bring useful capabilities to bear on important problems? We will spend the next few minutes exploring this question. Heart disease causes 25% of deaths in the U.S. every year. Heart arrhythmias are leading indicators of heart disease. Hundreds of millions of dollars have been invested in developing deep learning artificial intelligence that can reliably detect heart arrhythmia. While advances have been made, progress has been slower than expected, and there is the serious problem that deep learning cannot tell us why it has made a diagnosis. Direct learning artificial intelligence can be trained to make heart arrhythmia diagnoses in days rather than years. And critically, for healthcare applications, we can know why the diagnosis was made. Do we really need another form of AI? You need not take our word on this. DARPA is the self-acknowledged world leader in artificial intelligence. AI experts at DARPA are concerned that deep learning has significant issues that must be addressed by developing a new third wave of artificial intelligence technology. Let's take a look at what DARPA's concerns are and what their vision is. A state-of-the-art deep learning system tells us this is a boy holding a bat. And this result was after thousands of training samples and many hours of computational tuning. According to DARPA, deep learning is statistically impressive, but it is not reliable enough for many tasks. Deep learning is also complex and opaque. Deep learning is a mathematical beast and a font of intriguing challenges for artificial intelligence nerds. But DARPA calls deep learning spreadsheets on steroids that require highly specialized skills and a whole lot of time. A first principle in life as well as in engineering is that complex solutions are rarely the best ones. So according to DARPA, we need a third wave of artificial intelligence. The first wave, dating from the 80s, DARPA calls handcrafted knowledge. This is hard-coded algorithms that are still used today for many simple problems. The second wave includes deep learning, which has made great strides in tackling complex problems. But the bottom line for DARPA is that there's too much complexity and too little ability to engender trust. So late in 2016, DARPA announced an initiative to develop what it calls the third wave of artificial intelligence, contextual adaptation. Let's see what DARPA means by contextual adaptation and why they say it is needed. DARPA asserts that trust is a major problem with deep learning that must be solved by replacing or complementing deep learning with a new form of artificial intelligence. In the lower right-hand section of this DARPA diagram, you will see that DARPA envisions Wave 3 artificial intelligence will be faster, human-like, verifiable, contextually rich, adaptive, and correctable. We believe the future is already here in the form of Rokio's direct learning platform. In the next part of this presentation, we will explain how direct learning works and why it is important. To understand direct learning, we return to feature extraction, the first step in artificial intelligence processing. All AI starts with feature extraction. For real-world data, feature extraction converts the information from the sensors or cameras to something that can be processed by a computer. DARPA calls the computer end of sensor data a feature manifold. Think of a feature manifold as just the way a sensor perceives our world. Individual object types or classes form structures in the manifold, and direct learning learns those structures. Rather than processing the featured data in a complex, time-consuming, multi-layered neural net, direct learning starts and ends with feature extraction. Here are two objects in the DARPA feature manifold. Rokio's direct learning platform learns from the manifold by placing adaptive geometries on the manifold structures. Modern computers are very good at processing geometric data. Direct learning can take place in real time, eliminating up to 90% of the time and effort of deep learning. Direct learning begins with geometries. The geometries are adaptive, meaning that their size, we call it their influence field, adjusts whenever similar objects are learned. We call the geometries knowledge elements. A learning process results in many knowledge elements that together form knowledge bases. New queries are compared to the knowledge elements in a knowledge base in parallel sequence. Direct learning requires very few training instances to become effective, which is why we describe the process as show-and-go learning. Rokio has branded its direct learning platform Cure. Cure can learn autonomously or be expert taught. Let's take a look at how an expert teaches Cure. In this example, a heart specialist is teaching Cure to recognize a normal heartbeat and an important type of heart arrhythmia known as atrial flutter. The expert simply places a digital box around the portion of the heart rhythm that the expert wants Cure to learn. Once the box is placed, the expert clicks Learn. When done, the expert can test Cure's knowledge and, if necessary, do additional training examples until he or she is satisfied that Cure is recognizing the target portion of the heart waveform effectively. Once Cure is satisfactorily trained, the Cure knowledge base can be exported to be embedded on a device or to run in the cloud. In the runtime application, the Cure knowledge base retains the metadata regarding the expert trainer and learning example for each knowledge element, so any result can be audited and verified. This is particularly important in healthcare and is a significant innovation that is not possible with deep learning. Now we are going to see a demonstration of Cure learning a heart rhythm pattern in action.
This demo illustrates Cure's show-and-go learning. What you're seeing here is Rokio's waveform recognition application that is in use today in the life sciences industry. This application is used by scientists to process, measure, and recognize up to 1,024 channels of myocardiocyte heart rhythms. These are stem cells that beat like heart. Drug research scientists are increasingly using myocardiocytes to test for adverse reactions to experimental drugs. What you see here is two stem cell heartbeats in channel 1 and 2. There are recognizable heartbeats with a small P wave followed by a spike known as the QRS complex and a larger T wave. We're going to learn a T-wave pattern now. We do this by simply clicking Add Pattern, placing a box around the pattern. We'll label it T1. We right-click Learn, and now we're ready to see how we did. We're going to click Analyze, and as you can see, we recognized all the T-waves in this example. And if we want to see how we did against the second channel, we can tell Cure look at the second channel as well. And as you can see, we recognized all the T-waves in the second channel as well. Now let's say for some reason that we do not like the shortness of the trailing slope on a T-wave like this. So we do not want Cure to identify T-waves with very short trailing slopes. How we do this is we're going to teach Cure to eliminate this kind of pattern. We'll do that by clicking Counterexample. So now Cure has learned that this is not acceptable, but this is. So let's see how it does when we analyze. And as you can see, Cure has now eliminated a number of the T-waves with short trailing slopes. So what you've seen in this demonstration of Cure is that the knowledge base is ready for use and pattern identification as soon as we're done training. We can modify our training on the fly. We do not have to run a deep learning process. And while I did not show this, a user can easily ask why the T-wave is being recognized. Here we'll point to the original training example, who trained it and when. So we hope this simple show-and-go learning example gives you some insight into just how fast direct learning can be.
Now let's revisit our example of heart arrhythmia detection to explore how Cure can impact this important field. The use of geometries to build knowledge directly creates a number of capabilities that are important for heart arrhythmia detection. Experts who know their field extremely well can train Cure directly. Cure can export the knowledge base, which is small enough to fit on any device and function without the need for connection to any external computing platform or network, meaning that the wearer of a Cure-enabled arrhythmia detection device can get critical warnings wherever they are, in a big city, in a tunnel, on a rural road, or hiking in the mountains, increasing the utility of wearable devices that are otherwise dependent on internet connections. Crisis avoided. And importantly, the physician can always determine why a detection was reported. How does Cure enable DARPA's vision? From its very conception, Cure was built with simplicity, human-like learning, and human user trust as core objectives. Two of Cure's features, hierarchical processing and auditability, allow human users to answer a series of whys. Why should I believe you? Why are you giving me this answer? Who taught you that? Cure is also highly efficient. Cure learns directly from the sensor, requires few training examples, enables show-and-go learning. Cure geometries leverage parallel processors. Cure works with all types of sensors and incorporates critical trust-building capabilities. Cure creates efficient, portable, runtime applications that are embeddable or can operate in the cloud. Indeed, for real-world waveform, image, and video artificial intelligence, Cure addresses DARPA's vision directly on all counts. Now, perhaps it seems like we are bashing deep learning, but we are not. Let's take a look at the two technologies side by side. When should you use direct learning or deep learning? There are a number of distinctions between use cases where pure direct learning and deep learning would be most suitable. The highest level difference is that Cure is built for real-world data. That is, data acquired from sensors, cameras for images and video, and the myriad of sensors that acquire analog data from the stars to the dirt under our feet. Deep learning is built for a wider range of data, including, importantly, text and tabular data from conventional databases. We believe direct learning and deep learning will be complementary for a number of use cases. Cure is not an idea. It is a real, patented, and battle-tested technology developed from 2007 to 2016. During this time, Cure was successfully tested in a series of R&D projects with major companies involving both image and waveform processing. A Cure application for stem cell heartbeat waveform analysis is in commercial use today in the life sciences industry for adverse drug reaction testing. Rokio can provide white papers on these projects for those wishing to learn more. Today, Cure is hosted in the cloud, and Rokio is developing our first market entry. This will be a heart arrhythmia detection application development web service for healthcare experts and consumer product companies to develop heart arrhythmia detection applications. We expect this product will disrupt the market consensus that heart arrhythmia AI is difficult and costly. We will offer the arrhythmia detection development service for free. Our revenue from this application will be generated from licensing the exported knowledge bases. We also offer two products that emerged from the R&D projects described earlier. One is a 1024 channel stem cell arrhythmia detection application for life sciences adverse drug reaction testing. The other is an embedded DNA diagnostics waveform application that we believe can challenge the incumbent hardware-heavy DNA diagnostic systems in the market. Rokio is also engaged with a partner company that plans to launch a consumer application based on Cure in the sports performance and training market. Rokio's technology and business plan is to develop a universal feature extraction layer that will enable users to seamlessly import data from any image or waveform sensor directly to Cure in the cloud, and then to build applications, export runtime knowledge bases, embed them on their devices or place them in the cloud, and go to market. The result will be a universal Cure in the Cloud application development framework that will enable Rokio, our clients, and our partner enterprises to build knowledge bases for applications in a myriad of fields. Where is Cure Direct Learning likely to be very useful? Well, the answer is everywhere. Everywhere there are sensors or cameras, which is an awful lot of places and destined to become ubiquitous with the emergence of the Internet of Things, which is really the Internet of Sensors. Powered by the Cure in the Cloud application framework, Rokio will enable enterprises seeking to build real-world sensor-based artificial intelligence applications for embedded and cloud-based use. In addition to our heart arrhythmia and sports performance applications, Rokio will continue to seek partners with whom to co-develop proprietary applications. Rokio is focused on developing strategic relationships with institutions and enterprises that have large sensor-centric problems or real-world data intelligence opportunities that they wish to address. We have two initiatives underway and are interested in strategic discussions with entities in healthcare diagnostics, safety and defense, and the IoT infrastructure. Currently, Rokio is funded by its founders. We are planning to raise funds once our heart arrhythmia diagnostics development platform is released, which is expected for the second quarter of 2018. We appreciate your attention and look forward to answering any questions that you have. Please do not hesitate to call us or write us, or visit our website at rokioai.com.